Tuesday, and we are going to be working on the History of the Atoms notes part 4. Tomorrow will be the last of the notes, part 5. But they are actually quite challenging when we're talking about orbitals. So we are going to do that live. So tomorrow, Wednesday, you guys have live class starting at 9:10. That is how you'll get your 10 participation points. And I hope to see all of you there. Make sure you have your packet. Speaking of your packets, we just finished yesterday, History of the Notes Atom Part 3. If you go next, there is another worksheet, Atomic Structure. We had put this in the packet when we planned on everybody being back and making sure that nobody forgot how to do some of the atomic structure stuff. So the key to this is actually in the folder right beneath this video. If you do need it, it is there, so you can do that. And then I happen to have more practice, is always better. Atomic Structure Bell Work number 3. So let's have you guys turn to that. You can do worksheet number 2 if you would like, and check the key. You will have to be able to do these types of protons, neutrons, electrons, all that kind of good stuff, charge, full atomic symbol. You'll have to be able to do all that for the quiz on Friday and then for the test. So this never goes away. So I think what we'll do today is we'll start with Atomic Structure Bell Work number 3, making sure that you know how to do. I'll do a few on here, and then I'll just let you pause the program and check the answer key. So first thing you have to have is your periodic table. Looking good there. And let's remember a few things. So Z is the atomic number, or always tells you the number of protons. You probably have this information written at the top of your periodic table if you don't remember. A is the atomic mass. And what two things are in the atomic mass? Perfect. Protons and neutrons have to add up to give me the mass. And then electrons are the negatively charged particle, and the protons are the positively charged particle. And so what you're going to want to do is you look at the charge to figure out how many there are, and then you figure out the full atomic symbol. You put the element symbol, then you put the A and the Z and the charge. So I'll do a few with you, and then I'll leave you to kind of finish the rest of this on your own. So BE plus 2, so I looked this up. He's over on the left-hand side. I see that the Z is 4, so that means I have 4 protons. How do I get the number of neutrons? Well, 4 plus what equals 9, or you can just subtract those 2, and that will give me that I'll have 5 neutrons. Now, let's check out the charge. If I have plus 2, that means I need 2 extra positive protons, so 2 less than that would be 2 electrons. Then you put it all together. We have everything we need, 9, 4, BE, and then a plus 2. Let's have you guys try iodine, -1. So iodine, who's on the right, kind of almost down halfway through on the right-hand side. You see that he has 53 protons. Now, you don't want to always just take the mass off of the periodic table. I have 53 protons and 47 neutrons, so I'm going to add those together to give me 127 is my mass. And then I am -1 charged. So that means I want 1 more of these negative electrons. So if I have 53 pluses, 1 more than that is how many minuses to get to -1? Perfect. 54. Then you're going to put everything together. I goes in the middle, mass, atomic number, and then the charge. And then what I would like for you to do at the bottom here is says draw an example of an atom with Bohr's model. So what you're going to do is remember Bohr's model has the positive nucleus on the inside. And then remember Bohr said that electrons orbit the nucleus in these predictable little paths. So you can say the electrons kind of go around and around the nucleus. What element did Bohr's model predict the colors for the best? And we're talking about yesterday's spectrum emission line, little, however you want to call them, barcodes. Okay, And it worked best for hydrogen because hydrogen was such a simple element. You had one proton, one electron. It's not very hard to predict where that's going to go. Okay. Another question, do scientific models tend to become more simplified or more complex over time? And we talked about this in the notes last week, the very first notes at the beginning of Thanksgiving week. And we said over time, models become more complex, okay, because we gain more information, okay? First, we thought it was a marble. Then we found the electron. Then we found the nucleus. Then they found orbit. So it gets more and more complex. And so kind of the way that looks, if we start with Dalton, he said it's a marble. No pieces, no parts, no nothing, just a marble here. Then Thomson, he found that electron, okay, and he thought it looked like plum pudding. So we had positive mush here with little negative electrons in it. So it's already getting more complex. Then Rutherford did the gold foil experiment. And he found the nucleus, and he said that most of the atom is empty space, tiny little nucleus. Electrons must be somewhere out there. And then yesterday we talked about Bohr, who said that nucleus is there, but all of these electrons orbit in predictable paths around the nucleus. So, and then there's high energy outside and low energy closest to the nucleus. Okay, so kind of just rushing through that here. If you guys would like to finish, why don't you pause the program and finish the next three? And then once you're done, come on back and see how you did. All right. Hopefully you did well. Here we go. 10, 20, 10, 10. Put it together. 15, 15, 16, 18. And 19, 39, 19, and 18. Again, usually electrons are the biggest problem. If I have plus 15, I need minus 18 to get to negative 3. If I have plus 19, minus 18, that still gives me a positive 1. So if you guys got those done, awesome. You will expect to see more of these on the quiz and the tests in the upcoming Fridays. So let's go ahead and turn this now to, oops, wrong thing here. That's for the Thursday's test, or Thursday's lab. Extending Bohr's model to quantum mechanics. So it's Unit 4, History of the Atom Notes, Part 4. So one more turn in our packet here. Wonderful. So again, Bohr said that he had these electrons that orbit the nucleus. Orbit is the big idea here, like planets around the sun. We are going to find out today that that is not true. Okay. And what we needed, though, when we got to the mid-1920s, we realized that Bohr wasn't all the way correct. However, we needed somebody else to look at the problem and figure out an answer that we just didn't have. Okay, so the idea is that we knew that the electrons do not orbit like planets around the sun, but nobody can figure out how they move them. So what we had to have was somebody else to look at this problem in a different way. So this is usually a really fun lecture, and we talk about all these things, and so it's going to be a little one-ended on my side. But so what do you see here? Some people see an old woman, and some people see a young woman with a feather in her hat looking off to the side. So the old woman's kind of looking down here, but this is her mouth. And the young woman, this is like a necklace, and she's looking off to the side. So you can kind of see two things at once here. What do you see on this one? Do you see a duck or do you see a rabbit? Yes, both. The duck is looking that way, and the rabbit is looking this way with its ears back. Is the window opening in or is the window opening out? Interesting. Both. Cool. There's supposed to be three faces in this one. There's supposed to be an old man. He's kind of looking this direction, the old young lady, and then an old woman looking down. I don't know if I can see the third one, But again, looking at the same thing and seeing something different. There's two things. Some people see like an Inca statue this way, and some people see a person. Here's their hand, here's their feet, like waving off into the darkness. They're facing that way, so they're more like this. What do you see here? Some people see a shadow kind of face of a woman with a cast a shadow on one side. Some people see a guy playing a saxophone. What do you see here? Awesome. So some people see a figure of a person, but then you can also see the word liar. So both in one. So it's kind of interesting. So what we needed was for somebody to look at a problem that we had and see something else. Okay. So what we ended up having was a big question. Is an electron, the problem we're having is we don't think Bohr is correct, is the electron a particle or a wave? And the answer to that is yes. Okay, which is a very strange answer because it's either a wave or a particle. Can it be both? An electron is both a particle and a wave at the same time, depending on when you're looking at it. So that's why quantum mechanics is reserved for chemistry. And I was saying before, if you're walking around as a regular person and you think you understand Bohr's model and that's how atoms are to you, that's wonderful. Quantum mechanics that we're about to get into is a whole lot more confusing and therefore reserved for chemistry students. So we needed to have a new model, okay? And we call that quantum mechanics. Now, this is our current operating model. This is what we know so far until the next big discovery comes along and it changes again. But just like the marble and the plum pudding and the gold foil and all this stuff like that, we are now currently in the quantum mechanics model. So who helped us figure this out? Well, his name, the first name is Louis Victor de Broglie. He was working in the 1900s, and he was the first person to look at the picture differently and decided the electrons can show wave-like particles. So the little picture that I gave you here, it says P-A-R-T-I-C-L-E, or it also says wave. Okay, so the idea is that it can be both, which is really challenging to understand. So de Broglie's model was that there's that positive nucleus in the middle and that electrons were waves of negative energy that went around the nucleus. Okay. And of course, the nucleus is still positive nuke. So now we have a little bit more of an understanding, and some of our models are working a little bit better because it can be a wave, it can be a particle, it can be both depending on how it's acting at the time. And so then we still had an issue though with these little predictable paths. And so what you might have heard of Mr. Schrodinger, depending on where you are in your psychology classes, but Erwin Schrodinger came along and he was extremely intelligent, very into math, used math to explain everything. And what he did was he tried to investigate, like Bohr said, all of these things move in these predictable little paths. We should be able to predict where those electrons are going. Okay, so he set out to try to figure out exactly where the electrons are, and he developed a complex mathematical equation. Okay, he said, all right, so actually I pulled some of the notes out of a Georgia Tech lecture in quantum mechanics. And so this is Schrodinger's equation. Okay, and it starts off like this, and then, you got to go down and like carry the one or something. And then you go and you have a couple, other Greek signs, and then you keep going. And then now E is equal to that weird thing. And then you go through and you have your Hamilton operator, and then you have your momentum operator. Then you keep, this is all one math problem, by the way, still trying to describe where electrons are. So then he's going to keep going, and then he goes, and then your standard wave is one that's traveling, and then you go along. And so we keep going, we set up, and then you get to the end of his equation. And at the end of his equation, it says you basically have many possible states that can be occupied by the electron with different energies and different wavelengths. So in conclusion, we have no idea where an electron ever is at any point in time, which sometimes that can seem frustrating, but the idea is that orbitals were wrong. Okay, so sometimes when you learn that you don't know something, that proves that what you thought previously was incorrect. So back to your notes here. We have no idea where an electron really is. So the idea that Bohr said that you can predict these little predictable paths as the electron, just like planets around the sun, are absolutely wrong. No orbits, no orbits, no predictable paths. Okay. All right, so once Schrodinger blew up our predictable paths, how are we supposed to then know where an electron is? So we did have a couple more people come along. They're going to help us shine a little bit of light on that. And the first guy, his name is Werner Heisenberg. If you are into pop culture, you might have seen the series Breaking Bad. He calls himself Heisenberg, the main character, and they believe it is paying homage to this man. He was extremely intelligent, but he died at a very young age of cancer. And if you think about his law that we're going to talk about, it kind of might be another reason as to why this main character calls himself Heisenberg. So Werner Heisenberg wrote Heisenberg's uncertainty principle. Okay, and so he took all of Schrodinger's math, he put in some of his own math, and he basically decided that what you can do is you cannot know the position, which is where an electron is, or the momentum, where it is going, of an electron at the same time. So let's get that written down and let's think about that. With some of the technologies that we have now, we can actually get pretty good pictures of some atoms and parts of their electrons, things like that, so we can know where it is. But if you know where an electron is, you don't know where it is going. So if you say, hey, it's going this way, and then, so you don't know. So what we have to do is you have to use probability in order to decide where electrons are at any point in time around the nucleus. So going back to this here, we want to explain this if you think of a picture of a car. If you think of a picture of a car, a crystal clear picture of a car here, whoopsies, a little unoriented. Okay, if you saw this car right here, you would say, all right, you could know it's about, 3 feet from that cone. The back is about 3 feet from that cone. And it is, this far from the trees, and then that and the far end from the cone. So you could tell me exactly where the car is. Can you tell me if the car is going forwards or backwards? Or, because electrons don't just drive in straight lines, is the car going to lift up and blast into space? Is the car going to slide towards you, slide away from you? So the idea is the same with an electron. We can take a look at an electron and say where it is, but then once we know where it is, we don't know which direction and where it is going. On the opposite end, you can take a look at a picture where it's kind of the idea of like a zoomed, blurry picture. So this is obviously a picture where the car has passed. So we know that the car is going in this direction. Okay, we know that it's probably, if you had some markers, you could tell how fast it was going. If you knew like each of these is about a foot and you know how long the camera was open. So you could tell where it's going, but do you know exactly where that electron is? You don't. Okay, so Heisenberg's uncertainty principle says that you can know one of two things. You can know where it is, but then you don't know where it's going. And if you know where it's going, then you don't know where it is. So we have to use probability in order to try to figure out where they are at any point in time. So that's what leads us into our last part of the notes today, which are called orbitals. And I know it's kind of confusing because we have orbits and now we have orbitals. I think they were paying nod to Bohr to say, hey, you were kind of right, but maybe not all the way right. There are no more predictable paths anymore. That's not how we know how an electron moves around the nucleus. Instead, there are these orbitals, which are regions of space where there is just a high probability of finding an electron. Okay, you're not guaranteed to find an electron. It's just a high probability. Okay. If you were a betting person and I was like, I'll give you $1 million if you can go find a bee, you would probably go to a beehive, correct? You would say, well, here we go. Are you guaranteed to find a bee in a beehive? No. Are you guaranteed to not walk outside right now and then boom, there's a bee right there? Absolutely. So it's not necessarily definite, but if you had to guess probability wise where an electron would be, the electron is going to be in an orbital. Now, orbitals are what we're going to explain a little bit more tomorrow because, like I said, they're very challenging. Each orbital can hold 0, 1, or 2 electrons, but it cannot have more than 2. And so what we're going to talk about tomorrow is how they got these shapes. They basically took a bunch of pictures and they stitched it together and they figured out where their high likelihood of finding an electron. Okay, so orbits out, predictable paths are out. In are the idea of orbitals, and we'll explore those a little bit more tomorrow.